Okay, so we're entering the general discussion, but I'll continue to, because people have already had their hands up. Ted, did you have a comment? I saw your hands up.
Okay. No, I just had to check.
Katie.
Okay.
I was actually referring to Ted. Is Ted Jacobson?
I'm sorry.
Yeah, I'm not sure. Maybe my question has been covered, but Igor, you mentioned an analogous setup with the magnetic field playing the role of the gravitational redshift effect. And I just wondered, in your mind, like, what distinguishes those? It seems like it's really the same quantum mechanical phenomenon. So why should I care that in one case it's a gravitational potential that's causing the effect, in the other case it's a magnetic field? Is it teaching me something about quantum gravity? Given that analogy, it seems like it's not.
Thank you very much. I mean, it's a fantastic question. I'm very happy to clarify this. So it's in the same spirit as just normal time dilation. So forget even the quantum part. Any test of time dilation relies on the fact that your clocks tick differently at different rates. Now you can simulate clocks ticking differently with other means than GR. You can take a Swiss clock and Italian clock or so, and they will tick differently, just to give you an example. And so similarly here, you can induce the magnetic field, which also changes your spin precision. The special thing about GR is that, of course, it's universal. It has nothing to do with the mechanism of the clocks, which in this case happen to be spins. And then if you replace them instead by, atomic clocks, for example, this homogeneous magnetic field will not make them tick differently. And so this universal aspect is, of course, different. But the other aspect of the question is, does it teach us something about GR and quantum mechanics? It does not teach us about quantum gravity, but it does teach us, if we do it in the gravitational field, is that also the post-Newtonian corrections, which correspond to proper time, we can also add into the kind of normal description, which would not be surprising from the framework we have today, but it will be the first demonstration of actually doing that. So dynamics of systems with post-Newtonian corrections. And so I think it's a very important aspect to test. I hope this clarified the question.
Yeah, thank you.
Mariana?
Well, thank you for a very interesting talk. When you talk about clocks and superposition, it looks like you mean really clock states than literally as a clock technology, with sort of primary experimental proposals being more with atom interferometers. So I'm curious about whether there is any kind of experiment you can make where the clocks would, actual atomic clocks, and maybe not current clocks, but say clocks 20 years in the future, would be sensitive. So what would be your ideal clock experiment to test those ideas, and whether having a clocks in space on various say elliptical orbits would actually help? And thinking about, regardless of what the state of the current technology is, so what is it like you would like clocks to be able to do, to have larger separation, to be able to actually entangle clocks at different heights, whether that would actually be useful or not. So here I help just looking at the various possible proposals where clocks would be actually more sensitive than the interferometers, or it's really you're thinking about actually atom interferometers be always more sensitive to those effects.
Thanks also. I mean, it's an excellent question at the root of it. You're right that for the proposal, the actual clocks technology does not matter. It's just that you have dynamic degrees of freedom, and it could be anything. And in fact, even with the decoherence, you don't even have you have some thermal vibrations that don't even mean anything to you, but they decohere. And so that's why we focused initially on this atomic, because the separation is important. But your question is very, very, very interesting, and I don't have a very good answer. So for sure, I think clock technology as it develops will also be relevant. So for example, June talked about this delocalization and Bloch oscillations across, a lattice. That will become probably interesting, and that is one of the things we want to look at for sure. But if in terms of dreaming, of course, if you have like a very large lattice, over I don't know what centimeter scale or so, or even more, then it really might kick in. And if you go to space, on first sight, it might not help you because, gravity is, there's no gravity basically, so it's worse. But if you can entangle clocks, so we actually have a paper in preparation which shows that you can do a similar effect with entangled system if you do specific quantum operations. And so that might be, in fact, the best approach, because then you can really scale up separations to whatever you want. And you're just limited by how good can you do quantum control. And that is much, much easier. So excellent questions. And I don't have good answers, but I think what you're saying is outlining precisely what we will look at in the near future.
Thanks so much.
Okay. Arkady.
Okay, thank you. I'm still trying to follow. When you're talking about this kind of post-Newtonian correction, this time dilation, right? Then my understanding is that essentially it is kind of a check of equivalence principle, because you see you have this kind of say dependence on the position or whatever, but you can interpret it as a kind of change of the mass of the system, right? Because and then it leads to just interpretation of this time dilation, right? And I agree with what you mentioned about this universality, right? That what is specific is that you believe that it's universal, and in this way it influences your clock. But what I'm wondering about whether it, but this kind of universality, essentially it's classical even, right? It's not that even, it doesn't even call for quantum, but it still accounts for post-Newtonian because it's 1 over c square, whatever. So in this sense, I'm not sure if I got it right, that whether you have kind of, variation of this or difference there, because I would think that this kind of universality, this equivalence principle, it is kind of well defined in the case you are considering, or is there something kind of doubtful there?
Yeah, also a very insightful comment, and I think you're exactly right. And so these corrections that we look at the lowest order in the homogeneous limit, one can just as well obtain just by the universality and the equivalence principle. So that's exactly right, and there's no modification of it. It's a direct consequence of the equivalence principle, and this is the prediction. And this universality, of course, is classical, but it's in the prediction in the quantum domain that there's this additional entanglement effect that it will predict if you quantize kind of the degrees of freedom involved. So you're exactly right. And one can say, okay, so this would test kind of these principles in that limit and then see how these post-Newtonian corrections or these time dilation corrections start appearing. And if I'm just, let's say worried, I want to say, okay, but one really wants to go to a regime where the equivalence principle no longer is sufficient to predict it, but then the same effect still appears because only proper time matters, and you need to separate it further. And so then, a slightly different type of setup would have the same type of principle, but maybe then these corrections that enter are no longer sufficient just to do it in the homogeneous line.
Okay, but I'm asking it because it was this discussion about this UV completion of the theory, all the stuff. It's kind of not very much relevant to this point, right? I understood what you said about quantum mechanical appearance of these corrections. I agree with this, right? But in this sense, it's not like insufficient theoretical understanding at this level. I think it is sufficient, right, at this point. I see. Okay, thank you.
Yes.
Animesh?
Thanks, Igor. Very interesting talk. So just sort of a thought based on this discussion that you were having with, I can't remember who, about this magnetic field simulating the effect and sort of the effect of gravity on quantum degrees of freedom. Is there any known effect of gravity or gravitational curvature on the polarization of a photon? So if I sort of, instead of doing sort of all this atom interferometry, if I did sort of a polarization interferometry with photons, would one expect or should see something?
Thanks for the question. It's a very good question. It was our first thought, I think, after this 2011 paper to try and do it. if one wants to look at the same effect we look here, the issue with photons is that photons are on a null curve, so the proper time they experience is always the same. It's always 0. So you can never have like a proper time difference between photons and a polarization changing. However, so on the polarization, I'm not sure. First of all, there are other effects on the polarization, and there's other proposals which I think are very interesting. You know, other GR curvature effects that change polarization, and there are some proposals for space-based experiments there. Not from our group, but very interesting experiments. So that's one part of the answer. And the other is, if I wanted to see this time dilation effect, there is a analogous, or not analogous, but there is another manifestation of it. Namely, it's not that you experience different time, proper time, but the photons actually have a different path that they effectively move, and that's called as a Shapiro delay. And so the Shapiro delay is the same manifestation on this limit, namely that you know, as it passes close to the mass, it effectively is slowed down. But that just means it has, you know, much bigger, longer geodesic to go through, and that you can use for interferometry with single photons. And there are proposals. We had the first proposal on this, and there are some experimental proposals trying to do that. These space-based missions I mentioned are in this form, where you have a single photon interference along very large baseline, leveraging the Shapiro delay. And we have a paper on that from 2012, but it's not polarization; it's just their path coherence.
Okay, thanks. So just to clarify, so these effects that you mentioned, which I didn't know about, of the effect of gravitational potentials on the polarization, they would also count as evidence, or whatever you want to call it, of the sort of the interface of gravity and quantum mechanics. Would you say that then?
Absolutely, and in particular, I made this distinction of different types of interface. That would be also a test of quantum mechanics on curved spacetime. In fact, that would be really curved spacetime, because you do need, you know, really the geodesic precession or lens steering if you want to see this effect. And there are some papers in this.
Yeah. Maybe when you have a moment, maybe you can send me one of these references. Yeah.
Of course.
Okay, thanks. So before we leave for a break, there's a brief comment from Aita Tisinga in the chat window. Says these terms you focused on seem to describe the fact that the mass of an atom depends on the electronic state.
Yeah, thanks for this comment. That ties very well with some things that have been said. It's exactly right. That's exactly what I said. This is the manifestation of the equivalence principle, namely in combination with the special relativistic E equals mc squared. So because the mass of a system depends on the energy. And in other words, depending on what energy level your system is in, it actually has a different mass. And these terms I have appear because the different mass is a different gravitational mass. And so what Arkady, for example, said is that you can obtain these terms just from equivalence principle is precisely that. You postulate E equals mc squared, and then m equals mg, and then you can get these terms. So that's right. The system has different mass depending on what energy state it is in.
Okay, we will have a break until roughly 10 a.m. So see everyone. I'll see everyone then. Thanks. Bye.